All right, good morning. Morning. Let's go ahead and get started. So this last assignment, the assembler, was an interesting transitional piece. So you're still working directly with the machine language, but you were writing software to generate a program. And writing software to generate a program is most of what we're doing for the rest of the semester. The way to think about this conceptually is that we're operating in stages. So at the bottom, oops, let me correct for some glare here. Yeah, should be all right. So at the bottom, we have machine language. And this runs directly on the CPU. And of course, you know all about that because you've all now built some CPUs. And then above this, we have assembly language. And so the assembler that you just wrote performs this translation right here from assembly language to machine language. So we know that somewhere up here, we have a high-level language. And I'm sure you can visualize in your imaginations what it might be like to directly translate a high-level language to an assembly language. That said, although in the past many compilers were written this way, it doesn't really happen much anymore. That is, between the high-level language and assembly language is typically a virtual machine. That's what we're going to focus on for the next couple of weeks. So we're going to write a translator for a virtual machine that translates that into assembly code. And ultimately, when we write our compiler for a high-level language, it'll translate it into virtual machine code. So I'm first going to give some examples of common, well-known virtual machine languages that are out there to give you a feel for their role in the overall technology context. Then we're going to talk about details of the one we're going to create here over the next couple weeks. So, common VMs. One is the JVM, Java Virtual Machine. So with Java in particular, when you compile it, it generates JVM code. And those are referred to as bytecodes because each JVM code item is actually encoded as a byte that then gets translated on the fly by a JVM translator at runtime. That runtime JVM interpreter, though, is quite a complicated beast, and we're not going to attempt to do anything similar to it. What do I mean by complicated? So the Java compiler generates these JVM bytecodes, and then there are JVM implementations for different machines, Macs, Windows, and so forth. And the JVMs operate the same way in all of them, or they're interpreted the same way in all of them. But what happens is the JVM, as it's interpreting the bytecodes, will often identify this block of code is getting repeated a lot. So on the fly, it'll generate machine code for it. It's what's called a just-in-time compiler. So it'll generate an optimized machine code for sections of the program just on the fly. We're not going to be concerned with that, but I think there's a lot of value in knowing that that's out there. Closely related to this is the .NET platform from Microsoft, and its virtual language is referred to as the CLI, Common Language Interface. And this is the compilation target, for example, for the C# language that some of you might have been exposed to in a couple of our other courses. We use it in the game development class, and some groups use it in the databases class. So these are both virtual machines that operate as runtime interpreters. We're not going to be doing that. So a virtual machine that's strictly part of a compiler is called LLVM, and it stands for Low Level Virtual Machine, creatively enough. And LLVM is maybe a little closer to the kind of thing we're going to be doing in this assignment. LLVM is serves as a compiler backend for lots of different languages. So many different high-level languages will have compilers that generate LLVM code. And then there's this single backend that takes that LLVM code and turns it into machine code for lots of different platforms. So in other words, you can imagine saying, you've got a VM here, you've got language 1, language 2, language 3, and they can all generate VM code, and this in turn can generate code for ARM or Intel or what have you. And so virtual machine languages then have become extremely important for as compilation targets for high-level languages, to facilitate experimentation with and implementation of high-level languages, and to help support portability of those languages to many different platforms. So it follows then that when we're thinking about a VM language, it's going to have some aspects that are high level, and it's going to have some other aspects that are low level. It's going to have elements that feel more like a real programming language compared to assembly language. But it's also going to have elements that feel pretty assembly language-esque. So, and again, in many ways, it's going to serve as a bridge between things. So having kind of situated this and given it some context, any questions so far before we start to look at how our virtual machine is designed? Okay. Oh, yeah, Innocent.
So program the virtual machine, like let's say like a Haskell program, how does it compare?
Oh, Haskell absolutely uses a VM. So yeah, on the back end, the Haskell compiler generates LLVM code. So Haskell, for instance, is one of these languages out here that then gets translated into LLVM, and then machine code is generated from the LLVM translator. Yeah. Oh yeah. Haskell absolutely is targeted to a virtual machine.
So every programming language has a virtual machine somewhere.
All modern ones do. The difference is whether it's active at runtime or not. So with Haskell, the virtual machine's not active at runtime. It's just an intermediate target as part of the compilation process. So if you put a Haskell program into a Haskell compiler, what you get out at the other end is machine code. Okay. As opposed to Java or C# where you get strictly VM code and then you need to have a runtime installed. Yeah, you don't really need that for Haskell, but it still has a VM target as part of the translation process. Cool. Other questions so far? All right, so let's think about the programming model for this language. So this VM, like many VMs, is what is called a stack machine. So as I hinted at before, you think back to learning about stacks in data structures. Let's just say this is about to be Revenge of the Stack. You are going to be so fluent in stackness after this, it won't even be funny. So what's so appealing about a stack in this context? There are really two different things that make stacks appealing. First is it makes arithmetic easy. And we'll go over how precisely it does that in a moment. And the second thing it does is it makes functions easy. So having a stack makes arithmetic easy, bless you, and it makes functions easy. So I'll hint a little bit about functions today and Tuesday, but the main focus of this particular assignment is going to be the arithmetic aspects of using a stack. And so this assignment will be due next Wednesday, so 1 week after the assembly was due. So yeah, so we'll have some time on Tuesday to talk about this, these concepts as well. But yeah, for now, the focus is going to be on arithmetic. So in what sense does it make arithmetic easy? Well, let's consider an expression like the following. X plus y times z. So that nice simple expression. Somebody tell me the order in which it is evaluated. Yes?
Y times z and then plus x.
That's correct. Now, why is that? Anybody know? Yeah, Amos.
There are operation prioritiness.
Right. Operation precedence. Yeah. Oh, priorityness is a great term, but precedence is a difficult term. Yeah. So multiplication is said to have higher precedence than addition. So then if I do this, what's the order of events? Yes, Evan. Yeah, that's exactly right. And again, operator precedence is dominant. So, so here's the trick, right? You've got expressions like this in a high-level language. You can't just kind of execute them as you go. I mean, so that's one thing that's really clean and elegant about an assembly language, is that there is absolutely no ambiguity about the semantics. That is, you see the instruction, bam, it happens, you move on to the next instruction. In a high-level language, the actual order in which things happen doesn't necessarily correspond to the layout of the code, as many a poor soul in Computer Science 150 has had to discover, right? So you've got expressions like, x equals y times z, and students kind of get confused about the fact that this actually happens first, and then this part is actually what happens second, So a stack machine provides a way of bridging this gap, so to speak. That is, it's very easy to translate expressions like this into a stack-based language that preserves their order of operations. The stack-based language, in turn, is a lot easier to translate into assembly language than translating something like this directly into assembly language. So let me show you what we mean. Let's take this expression first, x plus y times z. And what we're going to do is imagine this expression being evaluated on a stack. So here's my stack. It's empty at the moment. So the first thing I want to do is to do a push. Specifically, I'm going to want to ensure that I push onto the stack the lowest priority items first, so that they happen last. So we're taking advantage of the last in, first out. Things that are high priority need to be pushed on last, so that they happen first. So the last thing that's going to happen is this x plus y, or this x plus y times z. So I'll push x onto the stack. And now I will push y on the stack and z on the stack. So now what I want to do is I want to multiply. So if I want to multiply, what I'm going to need to do is actually pop z and y off the stack, multiply them, and push onto the stack their product. So these guys get removed from the stack, they get multiplied, and now we have on top what I'll call yz, the result of multiplying them. So now my addition operator happens. And addition, so all of these arithmetic operators pop the stack, in effect. So when my addition comes in, I say, okay, well, I'm going to ship out x and yz. And then, they're both popped. And then I'm going to push back the final result of the expression. So that's what that one looks like. Let's look at this one next and get a feel for how it's going to be handled differently. So the lowest precedence operation is my y plus z, right? So I can imagine, or my x times y plus z. So I can imagine, oops, in this case, z actually goes on the bottom of the stack, and then y, and then x, and then I do a pop. So I pop x and y, I perform the operation x times y, and now it gets pushed back, and I've got x, y over here. Then, oops, plus comes along, it pops those two guys, performs that calculation, they're popped, and then we push that on the stack. So what this means is if we imagine what our higher level translator is doing, it's going to be able to use the stack to its advantage to provide a means of organizing the computation. And what's really nice about the stack-based arithmetic is the complete lack of ambiguity. Once I'm doing arithmetic with a stack, I don't need any parentheses. There's no ambiguity about operator precedence. You just put stuff on there and pop stuff off. You might even wonder, well, if that's so nice, why don't we just use stack arithmetic in high-level languages? And the answer is, it's been tried, and people don't like it. What do I mean? We're very accustomed to certain traditional ways of expressing things algebraically, traditional order of operations, and it's important that our high-level programming languages enable us to use those directly because that's what people want. It's the way people are accustomed to organizing things. There was once an attempt to build a high-level language off of the idea of a stack machine. The language is called Forth. It was kind of popular in the 70s, but kind of faded away. In general, people just prefer to have nice, standard, algebraic-looking things. So with the virtual machine, we just provide a way to easily map those expressions in the virtual machine space. So that's its advantage for arithmetic. What about functions? So we're not actually going to be implementing functions this week. We're going to be focusing on the arithmetic aspect. But I want to give you some context to appreciate why we're doing this. Okay? So the issue is as follows, right? In a Java program, you start with main. And then within main, it can call some other functions, right? So say it calls some function f and passes in some parameter. Well, what happens here is that main needs to stop everything it's doing and just wait. What's it waiting for? It's waiting for f to finish. Think about what a function call really entails. When you call a function, you're saying, I don't know how to do this, but this other function does. So I'm going to sit here. I'm going to metaphorically twiddle my thumbs and just sit here until that other function finishes. And then once it finishes, I'm going to pick up, I'm going to get its result, and life will go on as if nothing ever happened. What does this have to do with stacks? Well, think about it like this. I've started off by calling main, and you can imagine all of the state in main is on the stack. Now, when I say all of the state of main, I'm referring to lots of different things, right? For instance, what instruction am I on? What are my local variables? What are my parameters? All of that is actually parked on the stack. So then when I call f, it's f's turn. And it's got a notion of what instruction it's on, its locals, and its arguments. Maybe somewhere in the definition of f, which is elsewhere in the program, it calls g. So when it calls G, it also has instructions and so forth, and locals and arguments. And the point is, everything below G is kind of waiting on G to finish. But you just park it on the stack, and life is good. Because why? When G finishes, everything about it gets popped from the stack. And then F knows where it was, and it just picks right back up where it left off. So in other words, thinking about a stack and the last in, first out idea, in terms of thinking about how function calls happen, the last function called has to be the first one to finish. The first one called is the last one to finish. Man, it's hard to argue with a stack at this point. So this is what's known as the program stack, and we're going to explore some aspects of it this week and other aspects of it next week. So conceptually, we have a stack machine. The job of the stack is to manage arithmetic and function calls. And then by extension, it turns out part of the responsibility of the stack is to manage local variables and argument values. So our stack is a busy bee, actually. And the reason we're doing it is it makes arithmetic easier and functions easier. All makes sense so far? Okay, so having talked about virtual machines in general, having talked about a stack-based virtual machine and its rationale, we're going to begin to explore the specific virtual machine that we'll be implementing and what its commands look like. So we're going to start with what are called memory access commands. Now, there's life outside the stack, right? There's a main memory. We want to be able to talk to it. But if we're going to call a function or perform an arithmetic operation, it's always going to be in terms of the stack. So when we do a push, what we're going to do is to say, I want to push this value from somewhere in RAM to be on top of the stack. And when I do a pop, what I'm saying is I want to take the value at the top of the stack and store it somewhere in RAM. So the first two commands then to think about in the virtual machine are push and pop. But as I just hinted, they need a context. You're not just going to push from nowhere or pop to nowhere. They all need to talk to RAM. But the way they're going to talk to RAM is pretty different than the way we've thought about RAM so far. We are going to, for each of these, specify a memory segment and an index in that memory segment. So we're no longer going to be thinking in terms of main memory is this big flat piece of RAM. Instead, we're going to be thinking in terms of, in main memory, I can push things here and pop things from there, where here and there are regions that have purposes. And the virtual machine translator is going to have to take this notion of a segment and an index and translate that into a concrete machine address when it generates assembly code. What's nice about this scheme of having segments is that it's going to enable us to think about and to think in terms of the roles of various regions of memory in a high-level context. By itself, that probably makes no sense. So what I'm going to do is describe for you what the segments are and what their roles are, and then we can think about how that'll relate back to pushing and popping on the stack. So what are our segments? So a couple of these we've already talked about. The first segment I'm going to mention is called argument. Argument is a memory segment that represents all of the arguments that have been passed to the current function. So something that's very important about our virtual machine is that we are always inside a function. So a virtual machine program starts by launching a starting function. And from there, that function can call other functions. The point is, we are always inside a function. So if you think back to what I was saying about main, oh yeah, over here. Our virtual machine program will start off by calling main. And so it'll automatically have an argument segment waiting for it right there. There is a certain irony here in that because the argument segment is itself actually located on the stack, but kind of downward a bit from the top, you can actually push something that's within the middle of the stack onto the top while still leaving a copy of it further down. And you can actually pop things from the top and alter something that's happening within it. Don't think too hard about that, but it's part of what the virtual machine is going to do. So the argument segment is functions arguments. So the next segment is local. That's going to be the local variables for the current function. So the next one is called static. And the idea of static is these are variables that are shared by all functions that are in the same virtual machine file. So statics are kind of like global variables. I say kind of because the way that the system's going to be architected, you can actually merge multiple VM files into a single executable. So even static variables are local to the VM file that's being compiled. So ultimately what's going to happen is that in our high-level language, which is going to be a close imitation of Java, every class is going to correspond to one VM file, which will then all get merged together when it's time to create an executable. So the static segment is stuff that's visible to any function within the current VM file. Then there is what we might call a make-believe segment. And what I mean by a make-believe segment, this one only applies for push. And this segment is called constant. And we can use it for push only. And the idea of this segment is that when you give it an index, that index is just a constant that you're pushing onto the top of the stack. So if I say push constant 5, the number 5 just goes straight onto the stack. I can't pop a constant because I wouldn't want to be in a situation where 5 becomes 12, for example. If I say pop constant 12 or whatever, or pop constant 5, and then there's a 12 at the top of the stack, 5 does not become 12. We don't want that. So you can't pop a constant. It's not a real memory segment. It's just a convenient way to use the idea of a segment to get a constant into the system. There are still 4 more segments. So next we have temp. So temp has only 8 entries, and its intention is just to be every function in the program has access to this, and it's just a place to temporarily park a value that you just need for some purpose. So it's kind of scratch space. If you want to keep something around, don't just leave it there. It's sort of subject to death at any time. But temp turns out to be really handy when you're writing your compiler to stash values that are intermediate in a computation. Then we've got 2 somewhat weird segments called this and that. The this segment is a way of thinking about an offset into an object. So in a language like Java, right, you have classes and you've got objects of those classes, and each object of a class has a bunch of different data fields. So this segment just says, give me data field number 0, data field number 1, data field number 2, and so forth. That segment is an offset into an array. So when we're using the that segment, we're talking about array elements. And so the final segment is called pointer, and it's only got 2 elements. So pointer 0 controls what this is looking at, and pointer 1 controls what that is looking at. So every time you need to do an array access, you first set pointer of 1 to point to the starting point of the array. And then you can use segmentation to read and write values. So you would read by doing a push, and you would write by doing a pop. Same thing with an object. Once you're dealing with a specific object, you reset pointer 0, and that changes what this is pointing at. So these segments then provide a really nice conceptual framework for interacting with memory. Very, very handy. There are some things that they're maybe less good at. There's nothing about these that's particularly helpful when it comes to memory mapped I/O. And so what'll happen is that we're going to support instructions, even in our higher level language, to still directly access memory. We'll still need to do that. But most of our memory accesses can easily be handled in this manner. So, I mean, even this is sufficient for an arbitrary location. You can just put a starting point, say, for screen memory into that, and then treat where are you in screen memory as an offset, and so forth. So there are ways we can work even in that context. Yes?
In your structures, you implemented a start from like an ordinary array.
That's right.
You know, like you kind of went and sort of
Yeah.
it to make it work.
Yep.
And in this case, we're going to implement a stack virtual machine.
Mhm.
Are we assuming that we have a stack in place, or we're going to have to build it?
What do you think?
It's
What do you all think of Innocent's question? Is the stack going to be handed to you, or are you going to build it? Well, yeah, Paxton's right. We're going to build it. But you can still apply a lot of what you learned in data structures. And the reason is an array is just a piece of main memory. Right? That's all an array is. So here you're just going to be implementing the stack on top of the main memory. So when you look at it that way, it's not so bad, right? Just all very, very simple. Well, okay. Somewhat simple. So it follows then that we need to think about the relationship between the segmented memory arrangement I have just described and the RAM locations that are actually in our architecture. So a lot of what your job is going to be is to translate these push and pop instructions so that they do memory loads and memory stores. So let's think about what that's going to look like. So RAM regions. So I'm going to give a high-level overview of the different regions of RAM, and then we're going to take a low-level aspect of what's going on in each of these regions. So the RAM regions. So 0 to 15 are what we're going to call virtual registers. And some of these are going to have extremely specific purposes, like the stack pointer is going to be in there. Then 16 to 255, this is where static variables land. So the very first static variable will be at 16, the next one will be at 17, and so forth. Note that this is closely related to the fact that whenever you had a new label show up without any other binding in your assembler, you just started numbering it at 16 and 17 and so forth. Well, that's how we're going to implement static variables as well. Now, 256 to 2047, that is going to be where the stack is. You might be wondering, well, what happens if we need more space? And the answer is, that's just really sad. Anybody ever written a program in Java or Python and had a Stack Overflow? Well, this is why. In this approach to building a stack machine, you've got a region of RAM that's the stack. And if your stack pointer goes out of that region of RAM, it's out of luck. And so it just throws an exception and says, sorry, program cannot continue. Too bad, so sad. Here's the real issue, right? We like to program with a conceptual model of unlimited RAM, right? That's the conceptual model we employ when we're coding. That conceptual model is not applicable on any physical machine, right? It is not possible to build a physical machine with infinite RAM. Find a way to do that, let me know. But really, you can't, right? So one of the realities that I hope you come away from this class with is understanding the fact that RAM is limited. Anytime you write a program, it's physically constrained by the device. Our main memories have gotten so big that we hardly notice it now. You know, if you're sitting on 8 gigabytes of RAM, and then on top of that, it'll like park unused RAM on your hard drive in the swap space and so forth. Those kinds of details I talk about in my operating systems class. It can just be very easy to buy into that illusion, right? But it's not. Eventually it fills up. So typically in both Java and Python, in my experience, the stacks are big enough to handle about a depth of maybe 1,000 function calls. So when do you tend to get stack overflows, do y'all think?
Recursion never stops.
Yeah, when recursion spirals out of control is when you tend to get stack overflows. As a practical matter, recursion tends to be most useful when there's no particular danger of exceeding the stack limit. When does that happen? It happens a lot with algorithms that are like log n in some way. Like you typically want to do recursion tends to be most useful in an imperative language like Java or Python when the number of recursive calls is logarithmic in the problem size. Anybody remember any examples of algorithms like that from data structures where the recursive calls are logarithmic in the input size? Yeah. What's that? Merge sort's an excellent example, right? So y'all remember analyzing merge sort and finding that because you split the array in half every time, the number of times you split it is the log base 2 of the size of the array. So in order to exceed like 1,000 stack frames, you'd have to have an array with 2 to the 1,000th power items. If you can even fill an array with 2 to the 1,000th power items, more power to you. What's another example? Merge sort's a great example. What were some loggy things back in data structures? Binary search tree, great example. Traversing a binary tree is a recursive operation. you don't really want a binary tree with 1,000 elements or 1,000 element depth, right? You want your binary tree to be balanced. And in terms of having it balanced, if it's balanced, that means if its depth is 1,000, it's got 2 to the 1,000 items. Again, good luck even just filling it. So tree traversal also makes for a terrific recursive algorithm. Something less good is an algorithm that traverses an array, right? So it's pretty easy to write a recursive function that finds, say, a maximum value in an array. It's a bad idea to implement in a language like Java or Python because it is easy for that to be over 1,000 items, and the recursion can easily burn out. For various reasons, this stuff works better in languages like Haskell, which have a fundamentally different model for translating recursion. Yes?
You know, an algorithm like binary search algorithm, we are like binary searching an array, finding like an element somewhere.
Yep.
Can that cause that particular problem?
So binary search on a sorted array could be a great recursive algorithm because, again, you're only going to do log of the array size of recursive calls. So that's no big deal. Yeah. Of course, this adds an extra wrinkle to sort of the badness of quicksort, right? When quicksort spirals out of control and gets unbalanced, it's not only doing n squared, it's doing linear stack space. Yeah, quicksort. Anyway, so that's where our stack is. Then 2048 to 16383 is called the heap, but it's not a heap. So we have a region of memory that's called the stack, and it is a stack. Then we've got a region of memory called the heap, which is not a heap. It's not a priority queue. It's pretty much an undifferentiated morass of data. Specifically, though, the heap is going to contain objects and arrays. Objects and arrays. So in thinking about our segments, pointer is going to be in the 0 to 15 region, and it'll be changing this and that, which are then also stored in that region, but this and that will typically have references to areas in the heap. And then 16384 and up is going to be our screen and keyboard. So what does it look like within there? So we're going to start by thinking about 0 to 15. So a lot of our segments are specified in 0 to 15. 0 is going to be SP, the stack pointer. So the stack pointer is going to be pointing at the memory location where the next thing you push is going to be stored. So what do you all think the initial value of the stack pointer is going to be? Yeah. 256, right? So our VM code is going to have some initialization code that puts a 256 in the stack pointer. Okay? So initially, when the stack pointer is 256, there's nothing there, right? So what happens if you do a push? Well, you're going to do a store at 256. So if you push, say, a 12, 256 now has a 12, and the stack pointer is now 257. If I do a pop, I first subtract 1 from the stack pointer, and then I copy the value from the top of the stack to wherever its destination happens to be. So that's 0 is the stack pointer. 1 is the LCL, the local label, and this is going to be where the local variables are. 2 is arg, So this is pointing to the base of the argument segment. That's where the arguments to the current function are. 3 is this. And so that's the start of this segment. And that's for objects. Then 4 is that. That's the start of that segment. And that's going to be for arrays. So the pointer segment is just memory locations 3 and 4. So pointer 0 is 3, pointer 1 is 4. Then 5 to 12 is going to be the temp segment. And then 13 to 15 is up to you. That is, if you just need to stash a value somewhere, you can use locations 13, 14, and 15 to do it. No VM program will ever change those registers. So you just need a little scratch paper. That's the place for that. And then this temp segment will ultimately be scratch paper for the compiler. So that's 0 to 15. And as I mentioned, static, right, is just going to be starting at 16. So, oops. Let's go ahead and talk through the implementation then of each of these segments now that we've seen what the memory map looks like. So these segments are kind of in families that get implemented in specific ways. So let me tell you about these families, so to speak. So local argument, this and that are maintained by, they're mapped directly to RAM. So the idea is that you've got a dedicated register that stores its base address. So if we look back up here, we see we've got LCL, ARG, this and that, right? So if I do something like push local 1, what do I need to do? I need to look up what LCL is, right? So let's say LCL is 1000. Then I look at my index and I have to add 1 to it. That gets me 1001. So now I'm going to take the value at 1001 and I'm going to copy that to the top of the stack. Notice that when I push a value onto the stack, I just copy it to the top of the stack. And of course, I increment the stack pointer. Very, very important. I don't do anything to the value itself. The value is left alone. So that's kind of the first family of segments. And then a pop is very similar, right? So if I pop local 1, I do the same calculation, right? I find that local is 1000. I have to add 1. That gets me 1001. And then I decrement the stack and then copy the value to that memory location, that 1001. What these all have in common then is they represent indirect addressing. Indirect addressing. What makes it indirect? I have to look up where the segment starts in another memory location. So that's a level of indirection. So indirection is a little complicated to implement, but it's extremely powerful because just by altering what the start is of that segment, I can use the same instructions to do different things in different places. It's a very powerful, useful idea. Any questions then on the indirect addressing for segments? So next, oh yeah, Innocent. So if I pop local 1, I first look at the LCL register and find the value there. Let's say the value is 1,000. I just made that up. I then add a 1, that is the index. That gives me a final memory address, which is the address I'm actually affecting. To do the pop then, I subtract 1 from my stack pointer, and then the value that's now at the top of the stack, I copy over there. Yeah. So something funny about this, right, is even when I pop from the stack, I'm not doing anything to what was actually there. I'm only altering the stack pointer. That is, that value that was popped has been copied somewhere in memory, but it's actually also still sitting on the stack until something else gets pushed to replace it. So that's an important subtlety. So in the next two segments we're going to look at are pointer and temp. And these involve direct addressing. So what makes them direct is the fact that their offsets are fixed. They never change. So the base location for pointer is always 3. The base location for temp is always 5. Those are fixed. They can't change. If we look back at our map of this first region of memory, the purpose of pointer is to change these. And the purpose of temp is to change these right here. So coming back over here, we can say they are directly addressed. So if I do something like push pointer 1, well, that is absolutely going to location 4. If I pop temp 3, that is absolutely coming from memory location 8. No ambiguity at all. So pointer and temp are a little easier to generate code for than the indirect addressing segments. However, because basically no VM program is even going to work without the indirect addressing segments in place, you kind of need to do the indirect. You can't just do the direct ones first and then test it. You actually have to do the indirects early on. But certainly in my solution to this, I was able to do a lot of code reuse. That is, for all 4 of these segments, I really just had one code generation routine that specified what the address register happened to be for each of the segments. And I would just plug that in, depending on which of the 4 that it was. But otherwise, I generated exactly the same code. Right. Likewise here for pointer and temp, for these, I generated exactly the same code. I just plugged in a 3 or a 5 as the offset. Now, what's fun about these is you can actually calculate the final address at translation time. So if I've got an instruction like pop temp 3, I know before I even generate any assembly code that it's going to be location 8. And so it's pretty clean just to generate that straight away in your assembly code. Whereas for the indirect, you're going to have to perform an addition at runtime. You're going to have to generate assembly code that adds that base address from the register to the offset. So just looking at these, do you all find yourselves able to conceptualize what some of the assembly code is going to look like that corresponds to them? What kind of assembly instructions would you imagine generating for direct addressing? Like, say I want to do pop temp 3. Yeah, what's some pseudocode for what that's going to look like as assembly? Yeah, innocent.
Something like add 3, A, B, put A, get from there.
Yeah.
And
Right, you're going to be writing a lot of code. You're going to be generating a lot of code that looks like that. So right, each VM instruction is going to correspond to a good number of assembly language instructions. Like a lot. You know, these direct addressing pushes and pops, not quite as many. The indirect addressing, yeah, you're going to be generating a good number, which is fine. Yeah.
Are we gonna implement this in assembly, not in Java or Python?
You'll write the translator in Java or Python or whatever. The translator generates assembly code. So you're going to be processing this VM file just like you processed an assembly language file. So each line is one instruction. And then you're going to generate output, which is going to be multiple lines of assembly for each of those input lines. So it's very similar to assembly in that the control flow is very linear. One instruction per line, they happen in that order, you generate the code, you move on. It's going to be unlike assembly in that each instruction is going to turn into a lot of assembly language instructions. Yeah. Right, even something simple like a push or a pop with direct addressing, that's already going to be like 4 instructions. Indirect addressing is going to be more than 4 instructions. But it's going to be pretty easy to work out a template for what that's going to look like. You know, every indirect push is the same block of assembly code, just with a different register put in it, for example. And so what you're going to be doing in your translator is spitting out those multi-line blocks of assembly that correspond to a single input line. Other questions so far? Other questions so far? Okay. So constant. So this might be the segment you implement first. So push constant x puts x on the stack. You don't have to fetch anything from memory. You're just causing a specific constant value to appear on the stack. And then finally, we get static. So with static, like I mentioned earlier, you're going to exploit the labeling convention from the assembler. So here's what we suggest that you do. Every static variable with index j, so j is the static index. All you need to do is generate a label to represent it, which is the name of the, so your input file will be some file name.vm. So just generate a label, file.j. So by generating that label, file.j, it'll automatically be given a spot in the static memory, since the labels automatically get addresses starting at 16. Then the code you generate is basically just at file.j d equals m, and that gets the value for that static variable into the data register. And from there, you do whatever you need to do. And then similarly for a pop, you would just do the at file.j instead of d equals m. Well, yeah, it would be m equals d. So static is actually the last thing you're going to implement in terms of the test cases provided, but it's also really easy if you just take advantage of the way labels are set up in the assembler. It's as if the assembler was set up to make this simple. As if. Okay. Any questions so far? So this is all of the memory segmentation material. We're going to spend a little time now talking about the arithmetic stuff that you'll be doing. So here are the arithmetic instructions. Add, sub, neg, eq, gt, lt, and, or, and not. So there's a very nice chart on page 130 of the book that shows all these, and then page 131 has all of the static stuff. But I'm going to go over with you what this essentially ought to look like. So when thinking about the order of operations, you can visualize the stack in this way. So let's say it starts at location 256 and increases as we go down the page. So your stack pointer is pointing at this empty area waiting for something to happen. Then we're going to call the thing below it y and the thing below that x. So for adding, this isn't so important. So what add is going to do is it's going to pop x and y and then push x plus y onto the stack. With subtraction, you got to get the order right, because subtraction is not commutative. So you're going to subtract x minus y. In other words, you're going to take the value that's 2 memory locations below the stack pointer, and you're going to subtract the value that's 1 location below the stack pointer. Those go away. You then push the result onto the stack. Note that you don't really need to pop both values when you do these things. What you can do is just move your stack pointer up by 1 or down by 1. So move the stack pointer here, and then you can just do the math in place at that memory location. So in effect, you say, I'm going to get this into a register. Well, I'm going to subtract one from my stack pointer, get this into a register, and then I can just do the arithmetic using M, M and D. So if you get Y over here into D, then you can do D question mark M over here. And that results in fairly straightforward, clean assembly code that you're able to generate. So what about some of the others? Neg is going to have us have a negative y on the stack. So in other words, and so for these unary operators, you actually don't have to move the stack pointer at all. You can just change the value that happens to be at the top of the stack, using an ALU instruction. And so that's neg, and the other unary operator, of course, is not. And so that performs a not of y. In other words, you just flip all the bits. Right? You're ultimately using the ALU for all of this. But yeah, negative, not. So what about the others? Let's start with and or. These are obviously straightforward ALU operations. You just file them into the ALU, there you are. Kind of follow the same scheme I suggested for adding and subtracting, okay? What about these guys? So these are condition tests. These need to evaluate to true if their situation is as specified, and otherwise they need to evaluate to false. These 3 are harder to implement than the others. And the reason they're harder to implement is that you're going to have to implement them using some jumps. Why is that the case? EQ should push a true on the stack, which is, of course, -1 or all ones, right? if the condition is true. Otherwise, it'll push a 0 on the stack. And GT and LT will be doing the exact same things for their own operations. So what you'll be doing then is popping X and Y from the stack and checking to see if they're equal. To check to see if they're equal, what you're going to have to do is subtract them and then use the appropriate jump instruction to determine whether a given condition is true. So if you take X and Y and subtract them, and the ZR output on the ALU is a 1, then you're going to push a -1 onto the stack. Otherwise, you're going to push a 0 onto the stack, and so forth. Here, for all three of these, you're generating really similar code. And so I want you to know that it's completely legitimate to say, write a function that generates this exact same code, but with some holes in place where you can plug in the right jump instruction to generate it. You know? So this doesn't necessarily have to be a copy and paste festival, which is going to be hugely tempting. Hugely tempting. I encourage you instead to think about what's a general blueprint for the assembly I'm going to generate for this instruction, and how can I fill in the blueprint? So the same thing applies. So we might say, whoops, that these three follow the same blueprint. These four follow the same blueprint. They're going to be generating very similar assembly code. And likewise, these two are going to follow the same blueprint. And so thinking about those blueprints can greatly simplify what your implementation looks like. The overall skeleton of the implementation is going to be very similar to your assembler. You open a text file, you read it in a line at a time, you spit out assembly code. This one's actually somewhat simpler in that early on, you don't even need an explicit symbol table. You're basically leveraging the symbol table that the assembler has. You know, for this one, you can pretty literally read in instructions and spit out assembly code, which is kind of fun to do. It's not as simple as the assembler. In the assembler, for each instruction, you were creating a specific 16-bit pattern. For this, for each instruction, you're generating a bunch of assembly language instructions. In that sense, this is going to be a bit more complicated. But the control flow is actually simpler because every instruction has these stereotyped things that you just generate, just spit out straight away. So there are a bunch of test files provided. So going over to project 7. Simple add test. All you need to do to get that working, I think, is the push constants and add, and maybe there was a pop or something. Yeah, so I really encourage you to actually look over the input files, and as you build this, only add the instructions to your translator that are necessary to get that test case passed. So that's going to be a lot easier than just building the whole thing at once and then starting on the easiest test case. So I want you to examine like simple add.vm, see which instructions does it need, only implement those and see if you can pass. And then, yeah, so I think this is just constants and add. I think that was all it is. Stack test, now you're going to have your indirect addressing in here. So this is a nice simple test that really gets you started. This one is, there's going to be a big difference between your program that passes this and your program that passes this because of the indirect addressing. And then it gets a little bit more involved from there. You'll have the direct addressing, pointer test addresses that. And then finally, you'll have like everything working except static variables, and static test will address that. But I think what you're going to find is once you've done all of this stuff, getting to this point, you'll be like, statics? Boom. It was like 10 lines of code and you got it. And that's part one of the VM translator right there. Chapter 8 will be part 2 of the translator, which gets into setting up function calls and jumps in general. And so what I'm actually going to be doing with that one is breaking it into 2 deadlines. And the reason is that some of the initial tests are pretty easy, but then the later tests for Project 8 get a lot harder. And so I actually have those broken up into 2 different units that you'll be submitting at different times. Yeah, I'm sorry I didn't have your tests graded for today. I will definitely have them for Tuesday, though. And as I have them graded, I'll be putting the grades directly into Moodle. So once I know your test grade, it'll just appear. And then on Tuesday, I'm going to return them, and I'll go over them a bit. And we'll see where we're at. I haven't actually started grading them yet, so I don't know how it's looking so far. But I'll have them for you on Tuesday for sure. So that's the VM. Brief update on the test. Any last questions? All right. Have fun putting together your VM translator, and I'll see you Tuesday.